Download this code from codegive.com, link in the description below. Efficient runtime verification for the Linux kernel, a deep dive. Runtime verification, RV, is a powerful technique for ensuring that a system adheres to its specification at runtime. It involves monitoring the execution of a program and checking if its behavior conforms to predefined rules or properties. This tutorial delves into the challenges and techniques of applying RV to the Linux kernel, focusing on efficiency and practicality. 1. Why runtime verification for the kernel? The Linux kernel is a complex, concurrent, and highly performance-critical system. Traditional verification techniques, such as static analysis and formal verification, often struggle with its scale and complexity. RV offers a complementary approach, providing real-time monitoring and error detection without halting the kernel, in most cases. Here's why RV is valuable for the kernel. Detecting subtle bugs. RV can identify bugs that are difficult to find through testing or static analysis, such as concurrency issues, race conditions, and memory corruption. Enforcing security policies. RV can monitor system calls and other sensitive operations to ensure that they comply with predefined security policies, preventing unauthorized access and privilege escalation. Diagnosing performance bottlenecks. RV can track the execution time of critical functions and identify areas where performance can be improved. Ensuring correctness under dynamic conditions. The kernel's behavior can change depending on various runtime factors, hardware, load, configuration. RV allows for continuous monitoring and adaptation to ensure correctness in these diverse environments. Debugging production systems. RV can be deployed on production kernels, with appropriate safeguards, to detect and diagnose errors without requiring extensive debugging infrastructure or code changes. 2. Challenges of runtime verification in the kernel. Applying RV to the kernel presents significant challenges. Performance overhead. The RV mechanism must be lightweight to avoid introducing excessive overhead, which can impact system performance and stability. Kernel complexity. The kernel's intricate architecture, concurrency, and low-level details make it difficult to specify and monitor relevant properties. Instrumentation. Inserting instrumentation code into the kernel can be tricky, as it needs to be done carefully to avoid breaking existing functionality or introducing new bugs. Real-time constraints. The kernel often operates under real-time constraints, meaning that RV mechanisms must be able to react quickly to events and report errors without significant delays. Concurrency. Dealing with race conditions and shared resources requires careful synchronization and locking mechanisms in the RV infrastructure itself. Dynamic kernel. Kernel modules can be loaded and unloaded, and system calls can change with kernel updates. RV systems must be flexible enough to adapt to these changes. 3. Techniques for efficient runtime verification in the kernel. Addressing these challenges requires careful consideration of the following techniques. Lightweight instrumentation. Minimizing the performance impact of instrumentation is crucial. Options include probe-based instrumentation. Using kernel probes, K-probes, U-probes, etc., to dynamically insert monitoring code without modifying the kernel source directly. This minimizes the risk of introducing errors and simplifies maintenance. Static instrumentation. Adding monitoring code directly to the kernel source code, but only when necessary and with careful consideration of performance implications. This usually involves conditional compilation, if def, to enable/disable the instrumentation. Sampling. Instead of monitoring every event, Sampling can be used to reduce the amount of data collected and processed. This introduces a statistical element but can significantly improve performance. Efficient data structures and algorithms. The choice of data structures and algorithms for storing and processing monitoring data can significantly impact performance. Lock-free data structures. Minimizing the use of locks can reduce contention and improve performance, especially in concurrent environments. Lock-free data structures like atomic counters, ring buffers, and hazard pointers can be used. Bloom filters. Bloom filters are probabilistic data structures that can be used to quickly check if an element is present in a set. They can be useful for filtering out irrelevant events and reducing the amount of data that needs to be processed. Ring buffers. Ring buffers, circular buffers, are efficient data structures for storing a fixed size sequence of events. They can be used to track recent events and identify anomalies. Predicate abstraction and filtering. Reducing the amount of data that needs to be monitored and processed is essential for efficiency. Predicate abstraction. Instead of monitoring raw data, monitor predicates, Boolean expressions, that evaluate to true or false based on the data. This can significantly reduce the amount of data that needs to be stored and processed. For example, instead of storing the entire contents of a buffer, you might only monitor whether the buffer's length exceeds a certain threshold. Filtering. Apply filters to discard irrelevant events before they are processed. Filters can be based on event types, function names, or other criteria. Asynchronous processing. Performing monitoring tasks asynchronously can prevent them from blocking the execution of the kernel. Work queues. Use kernel work queues to offload monitoring tasks to separate worker threads. This allows the kernel to continue processing events while the monitoring tasks are being performed in the background. Kernel timers. Use kernel timers to periodically trigger monitoring tasks. This can be useful for collecting statistics or performing periodic checks. Domain-specific languages, DSLs. DSLs can simplify the process of specifying and implementing RV rules. Specifying properties in a concise and declarative manner. DSLs allow you to define the properties you want to monitor in a human-readable format, without requiring extensive coding. Automated code generation. DSLs can be used to automatically generate the instrumentation code and monitoring logic from the property specifications. This can significantly reduce the development time and effort. Kernel tracing frameworks, example Trace, perf. Leveraging existing tracing frameworks can reduce the effort of implementing RV from scratch. Using Trace for dynamic instrumentation and event tracing. Trace is a powerful tracing framework that is built into the Linux kernel. It provides a variety of features for dynamic instrumentation, event tracing, and performance analysis. Integrating RV rules into Trace scripts or plugins. RV rules can be integrated into Trace scripts or plugins to perform runtime verification based on the traced events. Modular design. Separate monitoring logic from the core kernel. This can improve the maintainability and reusability of the RV code. Provide a flexible interface for adding and removing RV rules. This allows you to easily adapt the RV system to changing requirements. 4. Code example, monitoring system call usage. This example demonstrates how to use kprobes to monitor the usage of the open system call. We'll track the number of times the system call is invoked and the most frequently opened file. Explanation. 1. Headers. Includes necessary header files for kernel modules, kprobes, memory allocation, and string manipulation. 2. Syscall_stats structure. Defines a structure to store statistics related to the open system call. Asterisk count, total number of open calls. Asterisk most underscore frequent underscore file, name of the most frequently opened file. Asterisk most underscore frequent underscore file underscore count, number of times the most underscore frequent underscore file has been opened. 3 open underscore stats global variable asterisk a static instance of the syscall underscore stats structure to hold the collected statistics. Initialized to 0. 4 open underscore stats underscore rusum reader writer semaphore asterisk a semaphore to protect concurrent access to the open underscore stats structure. Reader writer semaphores allow multiple readers to access the data concurrently, but only one writer at a time. This balances the need for data consistency with the need to minimize performance overhead. 5 open underscore entry, pre-handler this function is called before the ksys underscore open function is executed. Asterisk it increments the open underscore stats.count. Asterisk it retrieves the file name from the registers, regs-dir contains the address of the file name in user space. Asterisk it copies the file name from user space to kernel space using strncpy underscore from underscore user, important for security. Asterisk it updates most underscore frequent underscore file and most underscore frequent underscore file underscore count if necessary. Asterisk uses down underscore write to acquire the exclusive write lock before modifying the open underscore stats structure and releases it with up underscore write after the modification is done. 6 open underscore ret, post handler this function is called after the ksys underscore open function is executed. In this simple example, it doesn't do anything. Post handlers can be useful for retrieving the return value of the system call or for cleaning up resources. 7 kp, kprobe structure defines the kprobe. Asterisk symbol underscore name, the name of the function to probe, ksys backslash underscore open. Ksys underscore open is typically the actual system call implementation in the kernel. Asterisk pre underscore handler, the address of the open underscore entry function. Asterisk post underscore handler, the address of the open underscore ret function. 8 rv underscore init, module initialization. Asterisk registers the kprobe using register underscore kprobe. Asterisk prints a message to the kernel log indicating whether the kprobe was registered successfully. 9 rv underscore exit, module exit. Asterisk unregisters the kprobe using unregister underscore kprobe. Asterisk prints a message to the kernel log. Asterisk displays the collected statistics, the open syscall count and the most frequently opened file. Asterisk acquires the shared read lock with down underscore read before accessing the open underscore stats structure, and releases it with up underscore read afterward. 10 module metadata asterisk module underscore license, module underscore author, and module underscore description provide information about the module. How to compile and run asterisk. 1. Save the code asterisk save the code as rv underscore example.c. 2. Create a makefile asterisk create a makefile in the same directory with the following content. 3. Compile the module asterisk run make in the terminal. 4. Load the module asterisk run sudo insmod rv underscore example.ko. 5. Use the system asterisk open some files. The more files you open, the more data the module will collect. 6. Check the kernel log asterisk run dmesctail to see the output from the module, including the open syscall count and the most frequently opened file. 7. Unload the module asterisk run sudo rmod rv underscore example. The module's exit function will print the final statistics before it is unloaded. Important notes asterisk. Asterisk error handling asterisk the code example is simplified for clarity. In a real-world implementation, you need to add robust error handling to handle cases where memory allocation fails, user space pointers are invalid, etc. Security Be very careful when accessing user space memory from kernel code. Use strncpy_from_user or similar functions to safely copy data and validate pointers. Synchronization Protect shared data structures with appropriate locking mechanisms, spin locks, mutexes, reader-writer semaphores, to prevent race conditions. Choose the locking mechanism that provides the best performance while ensuring data consistency. Performance Monitor the performance impact of your RV code and optimize it as needed. Use tools like perf to identify performance bottlenecks. Kernel versions The exact system call names and data structures might vary slightly across different kernel versions. Adapt the code as needed for your target kernel version. Alternatives Consider using other tracing frameworks like ftrace or perf for more advanced tracing and analysis capabilities. These frameworks can often provide better performance than custom kprobe-based solutions. Hash tables The most frequent file logic can be made much more efficient by using a hash table, or similar data structure, to track the frequency of each file. This would avoid the need to linearly search for the file in each open call. 5. Advanced topics. Specifying properties with temporal logic Temporal logic, example linear temporal logic, LTL, can be used to specify complex properties that involve the order of events. For example, a lock must always be released after it is acquired. RV tools can then automatically generate code to monitor these properties. Dynamic adaptation RV systems can dynamically adapt their monitoring strategies based on the current system state. For example, the verbosity of logging can be increased when an error is detected. Integration with existing security frameworks RV can be integrated with security frameworks like SE Linux or Apermet to enforce more fine-grained security policies. Fault injection RV can be combined with fault injection techniques to test the robustness of the kernel under error conditions. This involves intentionally injecting errors, example memory corruption, invalid system call arguments, and verifying that the kernel handles them gracefully. 6. Conclusion. Runtime verification is a promising technique for improving the reliability, security, and performance of the Linux kernel. While it presents significant challenges, the techniques described in this tutorial can help to build efficient and practical RV systems. By carefully considering instrumentation overhead, data structure choices, and synchronization mechanisms, developers can create RV systems that provide valuable insights into the kernel's behavior without significantly impacting its performance. Remember to always prioritize safety and stability when working with kernel code. Carefully test and validate your RV implementation before deploying it in a production environment.